What's going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. We're talking about the 3 kinematic challenge labs, projectile labs that we've done over the last week or so. So we're going to start with our bomber problem, or our horizontal launch problem that we worked on earlier. Now, we started and we used a ramp in the first one, so the picture shows a ramp, but really with the challenge lab was to use our launchers, our mini launchers, crank them 3 times back, 1, 2, and 3, and then launch our marble across the room and determine the initial velocity of this launcher using only a meter stick. So I'm going to kind of write that challenge on the board over here. So our job was that we were supposed to determine initial velocity of the launcher using only a meter stick. No photo gate, no fancy technology, only a meter stick. Okay? And so here's what we did. We launched these objects, we set them horizontally, we launched them horizontally, and we took some measurements. We took some measurements for the height of the object, how high the marble was off the floor, and we used carbon paper and our plumb bobs to figure out what the range of this marble was. Here's some of the data we got. We said the height of the table, we measured this to be 0.98 meters, or at least I measured it to be that when I did this experiment. And I measured where it hit the ground after it kind of shot out of here. And I got it to be my range, or my change in x, was equal to 1.88 meters. That's how far away from the table it landed. And I'm asking you now to find the initial velocity of this launcher. So let's go ahead and sort our variables. Let's see what we've got. Let's make a list. I've got my x direction, I've got my y direction, and I can go ahead and say, like, what's my change in x and y? I've got initial velocity, I've got final velocity, I've got acceleration, I've got time. These are all variables that exist in both directions that I can kind of sort through. So let's think. I measured the displacement, the change in x, change in y, for both of these. And so for the x direction, change in x was equal to 1.88 meters. For change in y, it moved downward, so we can say that it was a negative 0.98 meters, because again, downward we call that negative. The initial velocity in the x direction, I don't know what that was. That would be this velocity right here, v initial in the x direction. That's kind of what I'm trying to find. This right here, this is the goal. Final velocity in the x direction, it's the same, there's no acceleration. So if acceleration is 0 meters per second squared, because there's no horizontal force acting on this object, well then this is going to be same as the initial velocity in the x direction. And a good picture with our forces on it shows us that. Okay? In the y direction, the initial velocity in the y direction is 0, because it's launched at a perfectly horizontal trajectory, so there's no initial velocity. It's essentially dropped from rest just with a little kick horizontally. And then we have our final velocity in the y direction. I don't know what that is. It's certainly not 0, because it does speed up as it moves to the ground. Gravity is going to accelerate this thing as it moves to the ground, so it's certainly not 0 at the end. But I'm not sure it matters right now. The acceleration in the y direction, the only force acting on this in the y direction is the force of gravity right now. It's an unbalanced force. It's in free fall, like we would say. So we know that this acceleration is downward at 9.8 meters per second squared. There's my acceleration. Now, these motions are happening independent of one another. What that means is that my x variables and my y variables, they can't crisscross. They don't really inform the other variables, except for one. We say this motion is simultaneous and independent. The independent part, keep our variables separate. But the simultaneous part means not just that they happen at the same time, but the motion in the x direction and the y direction have the same time. So they happen at the same time, which is more of like a visual representation. And our math representation is that they happen with the same time. So my variable, time, is actually the same, tx equals ty. And I feel weird calling it tx and ty because it's just time, but what I mean is time as it moves horizontally is equivalent, equal to, the same as time as it moves vertically. So the only way I can communicate between the x and y independent directions is through this time variable. So I'm trying to find my initial velocity in the x direction. It's moving at a constant zero velocity, or not, moving at a constant zero acceleration. So it's constant velocity, which means the only equation I can use in this direction is velocity times time equals displacement. Well, I don't know time, I don't know velocity, I do know delta x, so I'm trying to solve this problem, and I'm missing two variables in my equation. Luckily, one of those variables can be solved for using my y direction. So I'm going to start by solving for time in the y direction, translate that over to my x direction, and eventually find what I'm looking for, which is the initial velocity of my launcher, which is 100% horizontal velocity to begin with. So if I look at my variables, I know an initial velocity, I know a displacement, I know an acceleration, I know time. If only there was an equation on my equation sheet that related displacement and time given some kind of acceleration. Let's look. I see it. It's my second. It's my quadratic. That would be my relationship between distance or displacement and time. This equation is going to work for us. So I'm going to go ahead and say, I'm going to translate it over into my y direction. So in order to find time, we're going to use change in y is equal to the initial velocity in the y direction times time, plus 1/2 the acceleration in the y direction times time squared. This is my equation. This is my mathematical relationship between distance or displacement and time when an object accelerates. Let's start canceling, plugging, figuring this equation out. All right, my initial y velocity, that's 0. That term goes away. Delta y, I know. I'm going to leave that in there. And acceleration in the y direction is actually baby g. So I'm left with this equation here. Change in y equals 1/2 gt squared. Let's start plugging some numbers in. My change in y was negative 0.98 meters. 1/2 is a constant. Acceleration due to gravity is negative 9.8 meters per second squared. I'm trying to find time. I trust, or I'll let you do the algebra here, but I can multiply both sides by 2, divide both sides by negative 9.8. What I end up with for my time is 0.44 seconds. Is this my answer? Is this what I'm looking for? Not yet. Take it easy. I'm looking for the initial velocity of the launcher. But this is a missing variable that is in the equation I want to use. So now, if I look back in the x direction, and I see that I need a displacement in the x direction or a range and a time. If I have those two things, I can find the velocity in the x direction, which is the velocity of the launcher when it's launched horizontally. And hey, I measured that. I had a meter stick. I measured that the change in x was 1.88 meters. That's equal to the velocity in the x direction, times the time I just solved for. It's going to move horizontally for 0.44 seconds at a rate of 1.88 meters per second. What is that speed? I can divide them out. The velocity in the x direction ends up being 4.27 meters per second. And that is the answer to my challenge problem. What is the initial speed of this launcher? It is make sure you can see that point, 4.27 meters per second. I just found the initial velocity of this launcher not using a photo gate, not using any fancy technology, using only a meter stick and my understanding of horizontal and vertical projectile motion. Okay? This was our first challenge. The interesting part about this is that as long as I have this launcher and as long as I click it 3 times, the marble, regardless of the angle, will leave this launcher at a speed of 4.27 meters per second. And that's important heading forward. I've got a second challenge problem coming up for you, so if you want to try that one out, go check that video out as well. It's more of a cannon problem. We're setting up a cup, going through the apex of a launch and then into a cup. You can check that one out too. This was our horizontal launch lab. Let me know if you have any questions. Until then, see ya!